Good morning, one and all present here. Myself P. Janagarathina, Assistant Professor, Department of Mechanical Engineering, SNS College of Technology. In my previous video series, I already discussed about the basic introduction regarding heat transfer and the what are the types of heat transfers are available in our finite element analysis and all already discussed, and basic shape function equations of the heat transfers also already discussed. Today I am going to discuss about the topic on finite element formulation of the heat transfer element, which means the finite element equation for the one dimensional heat conduction problems. We already knowing the general finite element equations, which is F is equal to K into U for the normal finite element equation. Here the temperature problem we are solving, so F is equal to K into T, which means instead of displacement values, here we are calculating the nodal temperatures at the each nodes. So F is nothing but the element force vector, and K is nothing but the stiffness matrix, and T is nothing but the nodal temperature. So force element force vectors, it is denoted as the F1 and F2, and K is equal to AK divided by L. In our previous one dimensional problem, we are using the AE divided by L. So E is nothing but the Young's modulus of the given material. Here we are using the thermal conductivity K. Instead of Young's modulus, this is the temperature problem. So we are using the thermal conductivity K. So A is nothing but the area of the given element, K thermal conductivity of the material, and L is nothing but the total length of the bar, 1 minus 1 minus 1 1. Instead of displacement function, here we are using the temperature, nodal temperature matrix, which means the T1 T2. Okay, and this is the first case, one dimensional heat conduction with free end convections. We can consider the conduction with free end convection means we can derive this equation. Finally we will use these relations like this is the first case 1. We can consider the conduction with free end convection means H T infinity A0 1 which is equal to AK divided by L 1 minus 1 minus 1 1 plus HA into 1 minus 1 minus 1 1 plus HA into 0 0 0 1 T1 T2. A is nothing but the area of the element, which is denoted as the unit of meter square or mm square. K, which means the thermal conductivity of the element, watt per meter Kelvin, and L is nothing but the length of the element, and H means the heat transfer coefficients, watt per meter square Kelvin, and T infinity, which means the fluid temperatures which may be given in terms of either degree Celsius or Kelvin, and T is nothing but the temperature which may be given in terms of degree Celsius or Kelvin. The second case, one dimensional element with conduction, convection, and internal, we can consider the internal heat generation. This is the one dimensional bar element. Here one side we have to fixed, both side of the bar element will be fixed. Here the convection taken care, and the inside the element the conduction will be taken care. The node 1, the nodal temperature, which is denoted as the T1, and the node 2 which can be denoted as T2. So thermal conductivity and the internal heat generation. So consider a rod with nodes 1 and 2. This rod subjected to a conduction, convection, and internal heat generation means we can use these relations AK divided by L 1 minus 1 minus 1 1 plus HP L divided by 6 2 1 1 2. This is the nodal temperatures, and QAL divided by PHT infinity L divided by 2 into 1 1. This and all, the A means area, already discussed, thermal conductivity, length of the element, heat transfer coefficient, and the P is nothing but the perimeter value which may be given in that our problem, and T is nothing but the temperature K, and Q is the heat generation W, and T infinity fluid temperature K. This is the two cases of heat transfer problems we are solved in our finite element analysis. What are the procedures used to follow the solving of heat transfer problem means, first we can mention the number of elements. We are having the elements number is 1, 2 or 3. We can specifically mention the number of elements. After that we have to calculate the finite element equation for the each element. We are having 3 element means we can calculate the 3 finite element equations. After that we can assemble these 3 finite element equations. We can formulate the global finite element equations. From that we can develop the stiffness matrix K. From that stiffness matrix K we can follow certain steps to solve the nodal temperatures 1, 2 and 3. This is this general procedures to solve the heat transfer problem. So in our next videos we had discussed about the problems related to heat transfers, either 3 elements or 2 elements. Thank you.